So, the main concept to get from this is this idea that your electrons are going to flow from higher electrical potential to a lower electrical potential. Now, you're like higher to lower, but they're lower on the chart and they have a more negative potential. What does this mean? Well, it means that those electrons would prefer to get away from there and move to that positive side, which means the potential energy tendency is the exact opposite of the voltage. So electrons will flow to the more positive standard electrical potential because they want to create a cell potential that is more positive. And when you're calculating electrical cell potential, the cell potential is going to be your reduced species minus the oxidized species, because you're forcing this reaction to go backwards. So you're going to take the negative of that, a negative minus a negative, or you're going to force this one to go backwards. And it's a negative minus a negative, which creates a positive, which creates a highly positive E naught of the cell. So in order for this to be a galvanic cell, you need a positive E naught of the cell. Which means if you need to predict whether you're going to have an oxidizing agent or a reducing agent on something like, I don't know, your final, your strongest oxidizing agents are going to be the ones that have the most positive reduction potential. They're the ones that want to steal those electrons. Your strongest reducing agents are going to be the ones that have the most negative reduction potentials. So if you were to be given a set of materials and given their electrical potentials, you should be able to predict which one of these is going to be the oxidizer, which one of these is going to be the reducer, which one's the stronger oxidizer, those sorts of things. And like I mentioned, that entire chart is a relative scale based off of the standard hydrogen electrode. Because we can't actually measure the tendency of an electron to leave a particular material and flow into another one. We can't measure the tendency for a half-cell reaction to actually occur. But we can measure the tendency of one reaction to occur relative to another. And again, they chose the standard hydrogen electrode to correlate with the acid-base chemistry that we're all very familiar with. And so this is what most of the scales were built off of, but it's not necessarily the best choice. And so there are other standard electrodes available. And those standard potentials are of half reactions, and they are all of the half reaction as a reduction. Which means that if it is being oxidized in the cell, we're really looking at the negative of that potential, which is why when we write that formula, we're subtracting out the oxidized potential. And so that's what we're really measuring when we set everything up, is that change in potential. We're not actually measuring electrochemical potential. We're measuring the relative standard potentials. And again, we're in quant, so we can't really think of this as standard electrical potentials without bringing up the fact that when we're looking at standard conditions, we're looking at an activity, not a concentration, but it's an activity that correlates to a 1 molar concentration of the electrolyte species. Assuming the activity of all of the solids and pure liquids are at unity, and that the pressure associated with the production of any gases is equivalent to 1 bar. So for our standard hydrogen electrode, we have to consider all of those things. And of course that we're at standard temperature and pressure, so 25 degrees Celsius, 1 bar. And the way that the voltage readings work is that so long as the electrons are flowing from the anode to the cathode, you're going to get a positive reading because those are flowing along the natural cell potential. If you switch it up and you put your connections on the wrong way, you'll get a negative reading. It will be for the exact same value, however. So who has my battery? Ah, thank you, Elizabeth. So you want to hook your hot red lead to your positive side. Your black lead to your negative side. So the red lead goes on your cathode. That's where the electrons are going to. The black lead goes here. And my battery reads about 1.5 volts. And they're in contact really well. If I were to switch this, and so I put my red lead on my negative terminal, my black lead on my positive terminal, I get the same value, but it's negative. Okay. And so what your voltmeter is measuring is that electrical potential difference. And if your voltmeter is not having to add additional potential to get it to flow, it's a positive reading. If your voltmeter is having to add extra potential, it's a negative one. You're pushing those electrons uphill. But it's the same hill, so they're the same value. Pushing electrons up that hill, that's called electrolysis. We utilize electrolysis quite a bit as electrochemists. So we talked a little bit about how the idea of electrolysis is very similar to some of the concepts we use for anodic stripping and cathodic deposition, so that we can figure out concentrations of solutions that are unknown. We also use electrolysis to break down water into hydrogen and oxygen. Obviously, that's not a natural, spontaneous reaction that's going to occur, but if we apply enough electrical potential, we can cause that to happen. That's the concept behind fuel cells, is you break apart the water and then you utilize the recombination of the hydrogen and oxygen and the energy associated with that downhill flow to generate power. But again, it's all relative to this scale and those expected potentials. The potential that you would expect for any cell, as long as you're using a nice standard electrode, the standard hydrogen electrode, is going to be exactly what's read on this chart. But often we don't use the standard hydrogen electrode. We utilize 2 separate half cells of 2 different materials. And if we want to know what the standard cell potential for that case is going to be, we would want to look at the difference in the electrical potential from the positive terminal subtracted from the electrical potential from the negative one. And we're not changing anything from the chart. So that's something I really, really want to stress here. The cell potentials are the potential energies per unit charge. So they are an intensive property. We don't want to change any of the values on the chart. So if you are needing to balance these redox equations and you have to multiply one of those equations by an integer to get the number of electrons to match up, you're not going to multiply the reduction potentials to match that. All right, so don't change the values from those that are listed on the table. Same thing I want to stress is notice that this is minus the electrical potential of the negative, which is your anode. It's still the reduction potential that's exactly listed on the table. There is sort of a knee-jerk reaction where we realize that the reaction that's listed on the table is the reduction reaction, and that we are looking at the reverse of that, and that's the oxidation reaction. And so there's a tendency for students to want to take that value, make it negative, and then fill the negative value into this equation. They have already accounted for that for you with the negative symbol here. So don't change the values on the table. Just take the values for what you're looking at and fill it directly into this equation to get your E0 for your cell. And so if I'm looking at two half cells, one of them being zinc, one of them being copper, what I would do is I would go onto my table and I would look up the reduction potential for my anode, so for zinc. Zinc's reduction potential is a negative 0.76 volts. I would look up the reduction potential for my cathode, which for copper is plus 0.34 volts. Fill those values exactly as they are into my equation to get an overall cell potential of plus 1.10 volts. If you are curious as to whether or not you can use the materials you've selected to create a galvanic cell and how you would need to set it up in order for it to be a galvanic cell, so who needs to be the cathode, who needs to be the anode, for it to be a galvanic cell, it has to be a spontaneous process. So those electrons have to want to flow through the circuit. That's going to be a circuit that produces a positive E0 of the cell. Your non-spontaneous ones are going to be ones that produce the negative E0 of the cell. And so if I were to look at my copper and my zinc reactions, I look at the magnitude of the values here. And I think about if I were to add the opposite to the other, which one's going to create a positive value? And so for me, I see, oh, this is negative. If I add the opposite of that, that's going to give me a really large one. So I want the opposite of this. So in this case, zinc needs to be my anode or cathode. What's the question? Anode or cathode for zinc?
Anode.
Needs to be my anode. So the one that we want to run in reverse will be the anode. It's the one being oxidized. Whereas if I were to hook it up the opposite direction and try to force copper to be my anode, it's not going to be spontaneous. I can still make it happen, but I'm going to have to apply an electrical current and perform electrolysis to make that happen. So I want you to try that on your own. So I've pulled the electrical reduction potentials for aluminum 3+ to aluminum solid, and for chlorine gas to the chlorine ion. I want you to determine if the reaction of aluminum solid with chlorine gas to produce aluminum chloride is going to create a spontaneous reaction. And then I want you to determine the E0 of the cell for the cell exactly as it's written here. Try again.
You're doing that thumbs up for if you got it.
That works too.
I thought the food was good, so I was like, yeah.
Sorry.
Don't overthink it. All right. Are we there?
Yes.
Okay. So is it a spontaneous reaction?
Yes. It is spontaneous.
Très bien. So from aluminum solid to aluminum 3+, we want the opposite of that. We're going from chlorine, that's not staying the same direction. So the overall potential of my cell is 3.02 volts.
Did you make that positive because of like the equation and like minus whichever?
Which is also how I could tell that it was going to be spontaneous, because now I have a very positive number because this reaction is going in reverse. So what I recommend is that if you're comfortable memorizing the equation, I often think of the equation as this, and since I'm flipping that reaction, it needs to become positive.
I thought that the red, like the subscript, was because like the equation was written in red, but that's it for reduction. Yeah, reduction. I'm sorry, I just like wasn't sure why that was there, and I didn't want to ask.
Yeah, this isn't color. It's denoting reduction. All of the potentials in the chart are reduction potentials. To get the oxidation potential, you would change the sign of it. They take that into account by having a minus here, and then you just pull the reduction potential exactly as it is from the chart. But I don't really like that. It seems counterintuitive to me. And so I do the equation like this, and then I do stuff like that. So it's not so bad. It's a little bit easier than it looks like. And I can tell if it's being reversed if it shows up first here. Or if I'm given the reaction, it's the opposite direction of that reaction for that half cell. Does that make sense? Should I give you another one to try? Okay. So let's look at the cell that would be created if we were doing a sodium chloride half cell. So we're looking at chlorine and sodium. So plus 1.36 negative 2.71 is the reaction from sodium solid plus chlorine gas to produce sodium chloride. Spontaneous.
Yes.
Fantastically so. In fact, it's a very explosive one. It makes really cool green smoke. I'll show you a YouTube video in a minute of that. It's really cool. So yes, it's spontaneous, and I can tell it's spontaneous because what? Yes, we get fantastic green smoke when we actually perform it, based off of the cell potentials.
Yeah, so one's extremely positive and the other's extremely negative.
Yep, and we're doing the reverse of this one.
It's going to come out to a positive E naught.
Yeah, it comes out to a positive E naught. So my two half reactions in this case are sodium to produce the sodium ion plus 1 electron, chlorine plus 1 electron produces the chloride ion. This has a potential, it's the oxidation of this. This has a potential of this, which gives me an overall value of 4.07 volts.
In what case would it be like non-spun? Is it
Fantastic. She asked, what case would it not be spontaneous? If we were to,
if you were to use like two negatives or two positives?
well, it doesn't necessarily have to be. It has to be magnitudes.
So if we had both cells being the same thing, then nothing would happen.
Well, obviously.
No.
Gosh, Pete. But if we had
Baseline.
iron 3 plus an electron. Iron 3 plus O. Solid plus O2 gas. It's a lot harder to write when it doesn't work. Right.
Yeah.
Well, you do, but then they'll find the ones that don't work when they're flipped.
Right. Well, yeah, that one was.
Oh, yeah.
So while you're writing that, I've got a question about how these reactions proceed. If you have it set up so that it won't be spontaneous, wouldn't it just go the reverse direction and then become a spontaneous reaction? Or is it you have to actually set it up to be the correct way? Right. Oh yeah. Yeah.
Halen understood the question. Okay. So assuming this is an actual reaction.
Is it not?
I really don't think you're gonna perform. You can get that type of compound, but I don't think you can get these two.
Just point an arrow.
Yeah.
Yeah, so would these two spontaneously react?
No.
Why?
Because you wrote it up in the board.
Because when you asked me, it was one that wouldn't work.
It's because of the potential.
Yeah,
Because
They come out the negative count.
you should.
Let's do this.
If they're not spontaneous.
No. Yes. Producing. There we go. That's how that functions. Do-do-do. Perfect. Now I got it. So we're looking at
Oh, it's multi.
plus
Oh, wait.
2.87 and plus 1.36 is our reduction potentials. And so our half cells are iron, Fe, fluorine gas, plus 1 electron, producing 2 fluorine ions. Our other one is chlorine minus, and there's 2 of those, producing chlorine gas and 2 electrons. This has a standard cell potential of plus 2.87. I probably need to write the other way to make it actually work out. This would be negative 1.36. This one would work out. I'm telling you, it's a lot harder to write ones that don't work.
Yeah.
There, Jessica.
So,
Wait, I just wrote that out.
NaCl instead of NaF at the end.
oh, okay.
Yeah.
Yeah. Okay. So I was kind of freaking out about that sodium, but it stays in the same form. It stays
Yeah.
as that ion. So
Remember, just because it's present doesn't mean it has to be partaking in the redox reaction.
Yeah.
We did that one way back. Remember, sodium plus going to sodium plus. He's just hanging out. He's a spectator. So what are our half reactions for this one?
You've got
CO2 plus 2 electrons.
Gotcha.
Goes to 2
If you
CO.
go 2 Cl minus. And then F minus is going to go to 2 electrons and then F2. Yes.
What's your electrical potential for this one?
Negative 1. Oh, positive, just kidding.
Okay. What about this one?
Negative 2.
Which means our over naught E cell naught is what?
Yes.
It's a negative value.
1.
We don't do basic math anymore.
So is it going to be
No, because it's negative.
Thanks, George.
Read your mind what you're saying.
Just don't make electroplating reaction.
This would be an electroplating type reaction. This would be an electrolysis. If we wanted to force this to happen, we could add in the negative 1.49 volts and force this to occur. Good. Like it when that happens.
Jessica, if it makes you feel better, I read it.
I know, I thought it was
Me
just because the
too.
equation was written in red. And I was like, I mean, that's a weird way to denote it.
I didn't say
I mean, it makes sense in my brain.
Yeah. I didn't realize it was like reduction until you wrote oxidation on the other one.
I'm really glad that you said it out loud because I wouldn't have figured that out.
I have no idea.
Now I know. I'm going to go back and rewrite those all in purple. So the greater the difference is between the two materials we're looking at, the greater that cell potential is, the greater the amount of work it can do. So the AA batteries have two materials that are closer together on that chart than our car batteries do. which means we're looking at a free energy association here. How much energy can we get from them? And we already know that for a redox reaction, the free energy is associated to the number of moles of electrons being transferred times Faraday's constant, which is the constant that relates the coulombs of charge associated with a mole of electrons. So there are 96,485 coulombs of charge transferred during the migration of 1 mole of electrons, times our electrical potential of our cell. If we're looking at standard conditions, then we throw in the G naught, E naught.
So, a car battery is bigger than a small battery, like a small AA battery. And part of that is because the more material you have, the more high voltage it's going to be, and that comes from the N part of the equation?
Yes. It also comes from the fact that you don't want your car battery to degrade in the same amount a AA battery would.
So you want it to have a larger capacitance.
You want it to have more material to use before it gets run down. You also want it to be able to recharge effectively.
So the amount of material you have affects whether or not it's going to be able to recharge. I thought it was just had to do with what
Recharging efficiency. Some of it is not going to recharge effectively, but if we have a whole lot more, then
less is lost.
yes. Which means that since we have a relationship between delta G and E, we also have a relationship between our equilibrium constants as well as our reaction quotients for when our reactions are not at equilibrium. So if we're at non-standard conditions, we still have a way of calculating our electrical cell potential. So we can get our E naught from the chart and looking at the different potentials based off of the chart, but what if we aren't at standard conditions? What if we don't have 1 molar concentration of the solutions we're looking at? Well, then we need to go to the Nernst equation. The Nernst equation allows us to evaluate what our cell potential is going to be at the conditions we're in. And there are 2 terms involved in this. So the first term relates the cell potential to the standard cell potential. The second term relates it to that reaction quotient. Oh boy, geez, we're going way back now. Remember your reaction quotient, you figure it out exactly like you do your equilibrium quotients, it's just that we aren't at equilibrium. So our reaction quotient is the products raised to their stoichiometric coefficients over the reactants raised to their stoichiometric coefficients, right? I also want to remind you that if you're looking at the ln of Q versus Q, they have an inverse relationship. So as you increase the size of Q, you're going to decrease the size of ln of Q. So what are some things that we could do to increase Q?
Increase the product.
Increase the amount of product present, absolutely. If we decrease Q, what happens to the ln of Q? Decreasing Q increases ln of Q, opposite relationship. What could we do to increase the ln of Q? Increase the amount of reactants, which means that if we're looking at a cell at non-standard conditions, and we're told different changes in the ratio of products and reactants, or asked to figure out what would cause a change in the E naught of the cell, we should be able to identify, okay, if I add more product, this is going to become smaller. What's going to happen to the value of the E for the stem cell at non-1?
If your LNQ is decreasing or increasing, then the number of the should be
If your
So it's
LQ
gonna be-
increases, then your E should decrease because it's
Yes.
minus RT over NF times natural log of Q. So then that means if you increase Q, then you increase E.
Did you guys get that?
Wait, why?
Whoa.
Because if you're subtracting it, why?
So
An increase in Q is a decrease in L and Q. A decrease in L and Q is a decrease in E not subtracted, so that means an increase in Q is an increase in E.
yes.
Thank you.
Yes.
yeah.
If that makes sense.
That makes
Yeah.
sense to us.
So basically, if you have more products, you're gonna have if you have an increase in products, you're gonna have an increase in energy.
So if you have an increase in products, are you going to have an increase in energy? Remember, this isn't energy, it's your cell potential.
Oh, great. Sorry.
You have an increase in self, but then doesn't that relate?
It
back
will
to
bring
the-
it closer to this. What you want to look at is which of these terms is dominating your cell. If you have a positive cell potential at non-standard conditions, and I said I increased the amount of product present, which means I increased Q. Is this going to become more positive or less positive?
More positive?
What if I decrease my reactant?
More positive.
Oh wait, yeah, you're right.
What if I increase my reactant?
Or less positive.
Yeah.
More or less positive.
More or less positive? More or less.
less
Wait.
positive, right?
Okay.
What if I have a negative E? If I increase my product?
You're gonna get less negative.
Thinking.
Okay, so this means my L and a Q amount here is going to get smaller.
Yeah, so it's gonna be less negative.
It's gonna be more negative because you're subtracting the negative.
Oh, yeah, because it's.
Just kidding.
Because that's E naught. Okay.
No, yeah, I was.
Wait. Are you saying that E is E naught? Negative E?
Nope, just negative E.
That's.
Galvanic cell.
So it's
Sorry, we stepped on a we stepped out for a second. I'm speaking along the terms of galvanic cells only. So if I have a galvanic cell, what does that mean about this?
It's positive because it's spontaneous.
There we go. It's always
Yeah,
positive
Oh, okay.
under standard conditions. So for a galvanic cell where this is positive, if we have a positive cell potential for the conditions we're in, if we increase the product, that means we're increasing Q, which means we're making this term smaller. If this term gets smaller, that's going to become more positive, yeah? Because we're taking away less of it. If we increase the reactant, though, we're making Q small, which makes this term big. If we're subtracting more of the positive, that means it's going to be less positive, yeah?
Yes.
If we are starting with a negative standard condition, all right, which means we have a far enough change in the cell conditions that even though it would normally be spontaneous under standard conditions is no longer going to happen under these conditions spontaneously. If we increase the amount of product we're making, so we're making this term larger, what's going to happen to this one?
It's going to approach the standard value.
It's going to be less negative.
So 1 less.
Yes. I like to think of it in terms of what it already is. If we increase the reactants, we're making this term smaller. Q smaller, which makes this one bigger. So if this gets bigger, we're adding a larger negative number, which means this is going to become more negative. I think I want to get you guys to try that. So, using the Nernst equation, for this reaction, for the galvanic cell of sodium plus bromine producing sodium bromide, the E of the cell for the conditions I have is negative 1.2 volts. What happens to E if I add more sodium ions to the reaction? So I'm increasing the reactants, which means we're decreasing Q, increasing ln of Q.
It's getting further away from the standard. Yes. Further away from the standard.
So what's going to happen to E?
More negative.
We're starting at a negative value here. This has to be positive. Why does this have to be positive? What did I tell you that it's galvanic? Minus our initial sum of this term, still ended up being negative. So that means this is already bigger than that. If we make this even bigger, what's going to happen to this? It's going to become even more. I know this feels uncomfortable. There's a reason I'm going through it as much as I am. Okay. So what happens if I remove the sodium bromide?
It's going to be closer to the standard. Less than negative.
Slow down. Think it through. So I'm taking out sodium bromide, which means I'm doing what to the products?
You're taking out sodium bromide.
You're decreasing.
Right, you're removing products.
Decreasing.
Decreasing products.
Decreasing.
So it is going to be more negative.
More
also.
So it's more negative. Yeah.
Mhm.
All right. Yes?
Yes.
Okay. You should also recognize when you're considering these that you're really only looking for changes in the species that are undergoing the redox reaction. Remember, when we balance redox reactions, we'll sometimes add water and protons to balance the redox reaction, but when we're determining the impact on the cell potential, we only want to consider our half reaction species. So if this had been Na2O, to balance this reaction, I would have had a water over here and some protons over here.
From the island involved in redox reaction.
It is.
Oh, yeah.
The protons and the water aren't involved. So if I added protons, what would happen to E? Nothing. Okay? Make sure when you're looking at these that you're identifying who's actually involved in the redox. And those are the only ones that are going to impact Q. So those are the only ones that are going to impact our cell potential. So when you're looking at writing a cell reaction and finding the voltage associated with that reaction, you want to write out your half reactions. And in particular, you want to look at what the reduction half reactions both look like so that you know what you're looking for in the chart. But again, do not multiply your E's by anything. Write out your Nernst equation for the half cell reaction attached to your positive terminal. So who gets attached to the positive terminal in a galvanic cell? So it's cat, which undergoes reduction for a galvanic cell. Negative goes with the find your cell voltage. Subtract the left from the right. We use this idea of measuring the potential difference between a standard electrode and a solution for a lot of our instruments. You've already encountered some of these, but they're the ion selective electrodes. You've used the calcium ion selective electrode, but you've also used the most common ion selective electrode, which is the one that is selective for the hydrogen ion, which is the pH probe. And the idea of how these ion selective probes work is based on these measuring the electrical potential from a standard half cell that's contained within the electrode, sheltered from the electrode from a very thin glass membrane. All right, so for most of you who got to work with the electrodes in 105, 106, you probably also ended up with a broken electrode by the end of the semester where you turned it over and, hey, look, the glass bulb is shattered and you were getting really poor readings. That glass bulb is very important because what happens around that glass bulb is this scenario where that bulb is acting as an ion selective membrane. That ion selective membrane allows the cations generated from your redox reaction that's happening in your test solution to affiliate with the outer surface of the membrane, drawing in the anions that are present in that membrane towards that. You get a layer of anions built up on that outer membrane surface, creating a charge discrepancy. That charge discrepancy pulls ions from the inner electrode solution towards the inner membrane. We now have a charge discrepancy on two sides of a membrane, which means we have a potential difference. And that's what we're measuring when we're measuring these ion selective electrodes. We measure the difference between that outer electrical potential and that inner electrical potential. And there's solid state ones, there's gas sensing ones, there's enzyme sensing ones. The most important one is the pH sensing electrode. Because we're looking at measuring the electrical potential on both sides of that glass membrane, it is extremely important that we calibrate our pH electrodes. Why? Changes day to day due to pressures. What else?
It's a membrane, so there's going to be holes in it.
It is a selective ion membrane. You can get charge buildup on your membrane, which means you have to account for that charge buildup. What also happens when you have charges that are in an aqueous solution? There's an activity associated with that because not only do you have these ions in solution, but those ions are being hydrated. And so you get a hydration sphere around the ions in solution, and you have to account for the activity of those ions in the solution. And so in your electrodes, you can have these beautiful crystal cells of silica, which is an idea dispersion of everything. Or more likely, what usually ends up happening is because it's amorphous silica, you get regions of localized charge patches. Those localized charge patches are what are going to throw off a lot of your electrical potential measurements in your pH probes, because they're going to change the cell potential, that junction potential in those locations. So again, you can get that hydration layer, which is going to affect your results as well. Which means you're going to have a diffusion coefficient associated with your pH electrode, and it's going to depend on your electrode, on the day that you're using the electrode, what the electrode has been stored in, and what the solution it is that you're submerging the electrode into. So that's why you have to calibrate your pH electrodes. You have to account for these discrepancies that are going to be created because you're working with a hydrated glass sphere. We are limited in our pH measurements because for our calibrations, most of our standards, the best we can get is a plus or minus 0.01 pH measurement. There's a junction potential associated with that porous plug at the bottom of the electrode. It adds an increase in the uncertainty in that hundredths place for our pH measurement. If our solution precipitates, we're talking about silver chloride here, it's not a highly soluble salt. If that precipitates in the region of that plug, we're changing, or just precipitates and it doesn't get near the plug, but we change the concentration of our silver and chlorine ions, we're losing the certainty in our junction potential there. So we get junction potential drift. So the standard is that you really should calibrate your pH curve every 2 hours that you're working with the probe. There's also sodium. Sodium is very similar in size and shape to hydrogen, which means there is potential that your pH probe will read sodium as if it was a hydrogen ion. There's also the potential of acid etching of the glass probe. Acids can leach sodium ions from the glass bulb because, again, similar shape and size. And so you can etch the outer edge of glassware with the acid. Or if you're measuring extremely strong bases, same concept, they will etch that outer layer of glassware. And then if you don't allow your solution to equilibrate, so once you stick your probe into your solution, you're going to cause a shift in the activity of the ions around that electrical probe. You need to give it time to equilibrate. You get the hydration of the glass, which adjusts the junction potential. Temperature will impact it as well because temperature will impact the activities of the ions that you're looking at. And then if it's not cleaned. A really common thing that happens, especially in our general chemistry courses, is that students clean our pH probes very roughly. It is an extremely thin layer of glass with a tendency to break. If it doesn't break, even if you touch it with a Ken wipe, the potential of scratching the surface of the glass, because it is so extremely thin, is possible, and which of course changes the junction potential. And so these are all errors that contribute to the overall error of pH measurement, which is why any pH measurement is limited to the hundredths place and to about plus or minus 0.2 hundredths. That wraps up chapters 14 and 15. Those are the key points that you need out of those chapters. So we have to calibrate our ion selective probes because they're looking at activities of ions in aqueous solutions through essentially a glass ball. And so there's some potential issues associated with that. You should be able to calculate the standard cell potential and the cell potential at non-standard conditions and be able to evaluate what changes in solutions will cause to occur for that cell potential. So what we were doing with if I added product out, that thing, and balancing. Okay. We will come back on Tuesday and discuss spectroscopy. Thank you so much.